morning everyone. So this is my third lecture and I'll be covering these topics. I'll be demonstrating how to make geometry using Blender. Then I'll be discussing the use of snappyHexMesh and how it is used for refining, and then I'll compare Blender versus some other CAD softwares. So I'll be making the geometry upon which I am working. So let's open Blender first. So this is the XYZ or the Cartesian plane of Blender, and here we see that it is the object mode. Then there is view, select, add object. So we go to add, and first I would like to add a cone. So we go to mesh and then click on cone. So it automatically shows a cone. In the bottom it shows add cone. When I click on it, it shows the information like how it is constructed. So this 32 represents the number of vertices upon which the circle is divided. So let's increase that. So we see that the curvature has become much more finer. Then say so I need a radius of these two radius. The second radius was 127. It automatically converts into meter, and the height was 102 mm or 0.102 mm. Here we see that it is intersecting, so the origin is lying somewhere in the middle. So what actually is happening is that the depth is like 0.102 meter. So the center is in the center of it, like in the middle of the depth, and I want to place the origin on the smaller circle. So I'll move this cylinder by 0.051. But first I want this cylinder to be symmetrical about y-axis. So I have to rotate it first. Let's rotate about x-axis and see how it. So here we see that the y-axis, the green one is the y-axis, and it has become symmetric about y-axis. And then the location of the center I can so here we see that we have successfully set the origin on the smaller circle. The next operation that I need to do for my geometry is I need to extrude this face to form a cylinder. So we go to edit mode, and then this is the extrude functionality. So we select this face. Oh sorry, here there are three modes: vertex select, edge select, and face select. So I'll click on face select, and then I'll select this face. Then by clicking on this plus sign and dragging, it will extrude the surface. Now I want the extrusion. I want it 421 millimeters. So 419 millimeters. So we see that it is extruded. So this is my outer geometry. So next I want to include a sparger in the middle, through which inlet of a fluid will be taking place. So we can hide this temporarily, and then the geometry for that is actually a torus shaped. So this is a torus, and here again we see that the properties of the torus are listed. So this 48, let's see what happens by changing this. So let's do it 64, and the minor segments, let's increase them to 24. So it has done a much more finer geometry it has created. The major radius I am using is 13817, and minor radius is 0.005. Added into the cone. And I want this to be placed at somewhere in between. So I want to locate it at 0.146. It's taking in Z direction, I guess. So if we look inside, we see that, and the sparger is placed like this. So we now need to rotate it. Let's see rotation about x-axis, how it goes. Okay. So let me do a Control Z, remove it. So right now I have constructed another object for torus. Earlier I um, just used it for the same, inside the same. So okay, we'll continue this way. And
creating in the same cone.
yes sir.
Ravinder, you know how to create a separate geometry? As in mode, objective mode.
Okay, in object mode. Okay, okay. So we'll change the mode, and then we'll hide this, and then now we have the sparger, and its location should be somewhere here. In this torus, or this I'll name it as sparger. Now I will create a hole by performing a Boolean operation. So for that, how it works is I have to create another object, and then I will subtract the intersection of those two objects. So for that, to create a hole, I'll be using a cylindrical object. Create. Right. So here we see that it is now I need to move it so that it intersects with the sparger. So I will click on this and then use transform it in such a way along the x-axis to intersect on the sparger. We see that it has not completely intersected, so we can move it by changing the y axis. So now we see that it has intersected. Now we go to the settings and click on add modifier, and we see Boolean. So there are three options available. We will use the difference. So we first click on the sparger, and here we use the Boolean operation, and we choose the object as cylinder and then apply. Let's see it. So we see that it has created a hole inside the cylinder. Now we don't require this cylinder, so I'm going to delete it. I'll be creating only one hole for demonstration. When we zoom it in, what basically happened is the curved surface and the top surface of the cylinder has been created. So we don't want this, we only want this hole to be the inlet. So we go to the edit mode now, and we use the vertex option. We go to the vertex option, and then by pressing Control we can select all these vertices. we delete it, it is asking for vertex, edges, faces. I will select vertex. So we see that the entire geometry that was constructed using those vertices have disappeared, and only the hole is left. So now we want to make a face out of this hole. So we again go to the edit mode, and by pressing Ctrl and clicking on another vertex, it actually selects the shortest path between those two vertex using the control functionality. So I've selected the entire whole vertex of the hole, and then I press F, so it will create a face on that hole. So now I want to separate this from the sparger, as they both are different physical entities. One will be a wall which will hold the fluid, and this will be the face through which the fluid will be coming. So using the face selection mode, I have used this, and right clicking and selecting separate, I can separate this particular face, and I will name it as, let's say, inlet. And now viewing with the entire geometry, we can see that it is rightly placed. And this is the inlet that I have constructed. So this is the inlet. These are the entire walls of the bed, fluidized bed. And I also want to separate or make an outlet. So this will become the outlet of the system. This can be done by again selecting this face, like first going to cone. And I want to separate this also. So this becomes the outlet. And I will name the rest of the cone. So let's see how the rest of the cone looks. So this is the rest of the cone, and I will name it as walls. So I have overall created 4 geometries: wall, sparger, outlet, and inlet. Now I will save this. So I want to save it in STL format, which is easily readable by OpenFOAM. So I'll select ASCII format, and batch mode will be object. Name it let me see whether it has saved it or not. and saved.
Blender format getting saved automatically.
No sir, we have to save it also. So to save Blender,
To do that because sometimes you are exporting it crashes.
yes sir. So the extension for Blender format is .blend. So now this has been saved. So it goes by the name of FB inlet, FB outlet, B sparsion and FB walls. I want to rename it. So I have my 4 STL files. So next we see that how we are going to use it for meshing purpose using the snappyHexMesh dict. So here we see that we actually required a base block mesh for generating the mesh, and using snappyHexMesh we can refine it at the surfaces. So what this block mesh does is it creates an entire domain in which the entire STL file will fit in, and after that the snappyHex will perform certain uh, uh, perform certain or execute some commands by which it will generate a mesh along that geometry which has been created using which is present in the STL file. So so this is the basic structure of the OpenFOAM file, OpenFOAM case. The 0 folder actually contains the initial conditions, initial boundary conditions of all the field variables. The system contains files such as control dict, which actually controls what type of application we are using and basically the setting parameter of the simulation. And the FV schemes file contains like how the mathematical partial differential equations have been discretized. And here we also find snappyHexMesh dict and block mesh dict. The constant folder contains information that are something which is constant to the system, like turbulent properties and let's say gravitational constant. Apart from that, it contains 3 more folders. Like these 3 folders are not necessary right now. It is created after we execute some command. Let's just empty this. So in the constant folder and then in the tri-surface folder we place our STL files. We put our STL files over here. So now we have pasted the STL files in this, and now we have to do is we need to check whether the block mesh dict is actually containing the entire geometry or not. So my geometry was actually around varying from 0.0762, like like here it is shown. This was the actual geometry of the like this was the maximum radius of the geometry, and this was the maximum height. of the geometry. And here we see that we are moving from 0.54 and minus 0.02. So we are basically encapsulating in our entire geometry. So now we execute the block mesh utility. So we see that it has created a block. The next command is surface feature extract. What this command does is, let me execute and then show.
So looking for a cone.stl.
Okay, yes sir. So this is the surface feature extract file, and here I have placed all the STL files, the information of all the STL files: inlet STL, outlet.stl, cone.stl, and sparger.stl. But I have specified in this folder as one of the STL files as walls.stl. So it has worked for inlet and outlet, but I have to change the name. So I'm just going to delete this, and let's save this. So now when we again execute this command, so we see that it has executed successfully, and in this folder it has created a .emesh file that it reads for itself, and it has also created like around 52 files, so 13 for each. Now we go to the snappyHex dict. So snappyHex dict actually contains has three main functionalities. So first is castellation, snapping, and layer addition. So castellation is basically, now since we have created a block mesh and these STL files are inside that block mesh, and .stl files are basically having the information of surface. So wherever these surface will be meeting the internal meshes of block mesh, it will register that and create its own geometry by let me just check whether it is. So in the snappyHexMesh also we need to change this as walls. So walls. And we see that it has started to execute. So it will take quite a bit of time. So let me just show how this snappyHex works. So first we have created an STL file. So STL files will be having a geometry like this. And this height was around 521 mm, and this was the maximum length. of let's say this was 0.0. This was 762 mm, and this was also 762 mm. So what we did was we created first a block mesh file, we generated a block. So we see that it is from minus 8 to plus 8, and since we have converted it is in mm scale.
Mm will be 80.
800, sir. It is meters, 0.08 meters.
You multiply that by 1000, right?
Yes, sir. So this is actually 76.2, sir. So we are getting 80 into 80, 160, 80 plus 80, and this is around 0.54 plus 2, 0.56.
So you talk in so units are this is meters, right?
Yes, sir. This is meters.
You multiply everything by 1000 per meter.
Yes, sir.
So
So
540 and
so the range is
20.
5 yes, sir, 20. So it is 560. So this becomes 560 mm. So we have created a block of this size, and we have already meshed it in the block mesh files. So it has its own meshing done. But wherever what the snappyHexMesh does is, wherever this STL file or the surface data is present, it will automatically refine it on those particular locations only. The rest of the mesh, let's say the rest of the mesh is like this, and so let's say it is falling in between these two meshes. So this STL file will now be castellated, like these blocks will now be becoming like spotting on the surface only, these mesh. So we will having the data of this particular points, or but it will create only blocks only. It is something like that. This is what the castellation part does. The snapping part, what it does is, these surface and these blocks are now, these blocks then snap to the surface, and we get a surface like this in the final meshing. And what the layer addition does is, it defines layers around these surfaces only. It further refines the surface. We can see all these three individually. Here we see that the snappyHexMesh is done. So here we see that there are 3 time steps that has been created. The first one has the information about the castellated part. The second one is the snapping part, and the third one is the layer addition part. I guess it has done some, I have done some error because of that. Sir, this supposed to be, it's supposed to look like a cylinder, like the geometry was, the outer geometry, the cylinder and the cone.
Can you check the snappyHexMesh file? Did you change cone to walls everywhere?
Yes, sir.
Check it again in cones.
Yes, sir, I need to execute it again.
The snappyHexMesh command, does it run in serial or parallel?
Sir, it can run in parallel also. Yes, sir.
Because since it takes time,
Yes, sir.
it's worth exploring how to do it in parallel to
Yes,
save
sir.
some time.
Sir, I did that, but reconstructing it was becoming an issue, because so that's why I am running in serial only. In the tutorial, it shows how to do it, and it actually worked. But when I was individually executing the command, I was getting some error.
In the meantime, if you already have something that has worked in the past in the folder, you can show that.
Okay, sir. So this is an example I already performed. So here we see that
Can we also see the initial block in this case? If you go to 0.
sir, 0 is not available here. So when we zoom into it, we can see that there are still blocks. So what this actually means is that the surface was lying somewhere in between here, the STL files. So it has only done the castellation part, that is, it has only extracted the blocks which were intersecting the STL file. So this is the what the castellation means. In the next time step, the snapping is done. So we see that these blocks will actually meet the surface of the STL file. So these were the surface of the STL file, STL geometry. Let me show you what was in the sparger also when the castellation was happening.
Is the room booked after today? Fair enough.
So here we see what the sparger looks like. It is also made by some block, and when we go to the snapping timestamp, so it has much more refined the surface. And the third part is the layer addition part. So layers are available so here we see that it has created layers near the boundaries of the surface. Yes, sir. So how we are actually defining it is so this is the castellated mesh controls. So it says levels. So if we increase this level, the blocks will become shorter and shorter. Like
Basically, you will make the mesh finer.
yes, sir. So what happens is let's say this is first the block mesh, and let's say we have a geometry of let's say a triangle. So in this particular region, if we use that level of 2, so what it does is it will create this. Sorry, this is level 1 type of creation, and level 2 will be further refinement. So now it will choose these three blocks as the castellated part, and then using these parts in the next time step when we are snapping it, it will make this geometry. So this is how the snapping part works, and the layering is just around the surface. So that's how we get the mesh using the snappyHexMesh.
For running the simulations, I don't need to choose the final output after layering. I can also choose the output after snapping if I don't want.
Yes, sir. So that is available here in the starting. So if we set these things as false, so
It won't even create that.
so it won't even create that. So these three are the main functionalities that the snappyHexMesh file gives.
As compared to block mesh, why would I go for snappy hex if block mesh is available? What are the benefits of using this over block mesh?
Sir, block mesh we specifically need to specify like where the geometry or the surface of the geometry is. This snappyHexMesh will automatically select those points only. In block mesh you will be have to specifying all the points, and then you have to refine, like you have to do grading and all. But snappyHexMesh will do it much easily for complex geometries.
So with STL files,
Yes, sir.
can we use block mesh?
Sir, block mesh here it is used for creating a prerequisite or like setting the minimum size where the geometry is like it does not exist. Like
So I mean, I cannot create a block mesh with this STL. That has no meaning. So we created a block mesh
yes, sir.
initial that
Yes,
was
sir.
a cuboid, and then use snappy hex to.
Yes, sir. Yes, sir. Sir, the block mesh also exists here also. So block mesh is existing in this way. Like this entire part is the block mesh file. Like these entire meshing in the middle,
Okay.
it is actually generated from the block mesh only. But to get these complex geometries, we are using the snappyHexMesh, where we are snapping the surface, and even inside the torus also, like torus also we can see that it has done a very fine refinement wherever it was needed. I have also failed to mention like how the inlet looks. So we see that this is the outermost or the base kind of mesh, and the inlet mesh, we'll see it. This is from the example. So in this inlet grading has not been done. So here we see that inlet will much more get refined and will represent much more actual geometry along with that mesh.
So Helix also uses snappyHex.
Yes, sir. So Helix also uses snappyHexMesh, but I was not able to, directly get what the kind of refinement through it, through Helix.
Helix is the front end.
Yes, sir.
The back end, it's I think using these things.
Yes,
Only.
sir.
If you can control the back end, then you have more control over it.
Yes, sir.
Good. Done?
Sir, I have one more slide. Like I was searching, like what is actually what Blender does and what the other CAD software does.
We can discuss. Nobody is waiting. So if you want, I'm okay.
Yes, sir. So in engineering, we generally tend to use CAD, but this time I used Blender for the creation of geometry. Blender actually is something which is used for graphic designer, to create animations and visual effects. It can be done much more easily on Blender, whereas CAD is used for creating or modeling engineering problems, such as which can be used for manufacturing and product design purposes. So the basic Blender file uses the extension is which are used by gaming and animation videos. I don't exactly know what these extensions are, but the CAD extensions are like STL and OBJ, which are widely used. One of the major advantages with CAD is that it can be integrated with modules which can do finite element analysis and let's say CNC machining. So these are the advantages of CAD. And precision wise, CAD is also better because it uses mathematical formula to define a particular geometry, whereas Blender is using like vertex and faces to create that geometry, like polygon modeling. It's called polygon modeling. And these are the basic differences that I found about Blender and CAD.
So CAD, what I've seen is that when you make, for example, Gmesh you were doing,
Yes, sir.
when you make circles or cylinders, it is super smooth.
Yes, sir.
But with Blender, you always have to specify the number of steps.
Yes, sir.
And everything is interpolated, like piecewise linear
Yes, sir.
interpolation.
Yes, sir.
So is there something in the heart of it that is different between CAD and Blender in that aspect?
Sir, that is what I guess is something which is the mathematical formula. Like for circle, it is using the definition of circle.
Basically, to store the information of circle, it is using the information like
Equation of circle.
equation of circle. But here everything is
vertex way. Yes, sir. Yes, sir.
I think for Blender is still okay with us because ultimately, even if he makes super smooth things, we will mesh it.
Yes, sir.
And once we mesh it, that information that we are
Yes.
after meshing, the information we have is vertices, surfaces,
Yes,
and
sir.
volumes.
Yes.
So in that way, Blender gives us more control over vertices
Yes,
and
sir.
surfaces and
Mhm.
problems. Right?
Yes, sir.
So it's good and bad, but I think
Mhm.
for CFD,
Yes,
if
sir.
somebody knows how to
Mhm.
control things, then
Yes,
Blender
sir.
can be quite
Yes,
useful.
sir. But we have the advantage to control at least how many points we can, or how many vertex we can do in Blender to, super fine, like not exactly accurately, but we can come close to accurate.
So let's say for the inlet,
Mm.
inlet was created by taking the difference between some geometry and the
Yes.
cylinder that you had.
Yes, sir.
So in that cylinder that I was using for creating the difference,
Mm.
if I had more number of points to define the surface,
Yes,
then
sir.
the inlet also becomes much finer.
Yes, sir.
And then if the inlet has much more number of vertices,
Mm.
does that mean that when I use snappy hex on it,
Mhm.
it becomes very fine?
Yes, sir. It can do that. Yes, sir.
So that is connected. I mean,
Yes, sir. That is
choosing
connected.
the number of points on the cylinder while
Mm.
taking difference
Mhm.
is connected to the final
Yes, sir.
snappy hex fine mesh
Yes,
fine.
sir.
And anyways, we could automate this process.
Sir, which part, like creating a file in
The
Blender?
process starts with doing some things in Blender, in
Mm.
GUI,
Mhm.
and then ultimate output is these OpenFOAM snappy hex files.
Yes, sir.
So could there be a script
Yes, sir.
that could be fed into an executable,
Mhm.
and then the output would be these final files of OpenFOAM.
Yes,
And
sir.
then I can control things in the script. So in the script, I could change the number of points I need for the circle, for that cylinder surface,
Mhm.
and then that I run the script, it
Mm.
automatically gives me output. So
Yes.
nobody has to manually do all the steps again.
Yes, sir. Yes, sir. Sir,
I'm just
of,
asking, I
of
don't know.
creating, like it can be done for snappyHexMesh and executing block mesh and all, but how to create a particular geometry in Blender, it can be something that.
So Blender has scripting in it.
Acha.
I remember when I was exploring it,
Mhm.
in the beginning, I got an idea of using Blender from this. There was a YouTube video on artificial intelligence and CFD and CAD modeling.
Mhm.
So Blender has scripting in it. So what somebody did was to chat GPT.
Mm.
It said create a sphere with certain size and
Okay.
because Blender can do other things as well. It can create lighting for
Mhm.
animation and all. So that person wrote a prompt,
Mm.
and the output was a Blender script.
Okay.
And you could copy that script. In
Mm.
Blender, there's an option of scripting. You click it, put
Okay.
the script in, say run, and it creates that thing.
Yes, sir. Then it can be done.
Right? So
Mm.
I mean, it's worth exploring. I have not done that.
Mm.
That is a separate thing. That
Okay.
I tried doing it, but I could not figure out.
Okay, sir.
Probably you can. So it's worth looking at it. If
Okay.
we can do that, if we
Mm.
can somehow record all the buttons that we are pressing into some sort of a script,
Mhm.
or maybe write a script. In the beginning, you may have to write a script, spend some time,
Mm.
but then the whole process becomes
Yes, sir.
automated.
Mhm.
Blender seems to be having a lot of potential in it.
Yes, sir. It is like very easy to
Do you
learn.
feel that it's in a way better
Mm.
and more comfortable to use Blender than Gmesh?
Yes, sir.
Gmesh is CAD, Blender is.
Uh, yes, sir. I have more control over the geometry in Blender.
So if you had to work with complex geometry, you'll prefer Blender.
Yes, sir. So we see that it took 658 seconds. So now we see that it has, it is reading those surfaces. Again, we are right now looking at the castellated mesh, and then we, in the next time step, we see it has snapped to the surface, the meshes, and the last one is actually layering. So what the next step would be, it would be like these are the files that has been generated. So this is the last most file. If I use the command snappyHexMesh -overwrite, then it will create only one folder which will have the final let's say layers like this the third time step. It will have the information of that only, and if we set let's say add layers as false, then it will have point 4 or the snapped part. So this thing actually contains the entire information of the geometry. So this folder needs to be shifted to the constant folder where the uh, so once we have pasted, now it has the information of the last time step of the entire folder. Now we can continue with the execution of the application of the solver.
This is going to be the next lesson.
Yes, sir. In that case, I will be demonstrating like how can we, what are the folder structure of OpenFOAM and what are the things that I've done.
Good. Questions?
Blender.
Every time, like before you showed us the demonstration that you have done earlier, so in that you had the folder name P2, P3, P4. So every time we have to like rename it to 0.002, 0.004.
No, it is not necessary. I did it for my own purpose so that I can execute again and it will generate same folder names like 0.002.
So if it is to be P2, P3 and P4, then it will also run.
No, the thing is that it is generating these kind of names is because I have set it in the control dict file. I am actually using this application solver as for solving the problem, and if we say like this delta t to be 1, so it will create 3 folders 1 2 3, and the third one will be having the add layers mesh.
Changing this value of delta t from
uh,
to a higher value,
uh,
does that have an effect
no
on
sir,
the mesh?
no sir, it actually basically represents like if we set it 2, then the folder 2 will represent the castellated part, then it will again generate a folder 4 which have the snap part, and then it will generate 6 which will have the add layers part also included. So I haven't changed it because I am using this 0.0002 as my delta t in the simulation, so that's why it has generated. But if we use that snappy hex mesh minus override, then we only get one folder.
With 0.0002.
That I'm not sure.
I guess 0006.
I'm not sure. I'm not sure about that.
But that doesn't matter.
And
Ultimately, you copy stuff and start from zero again.
but ultimately, to run, we have to put it in the constant folder.
So it starts from zero again.
Now we give the command, let's say 2-phase Euler form. So it will start from this. It will start from this folder now. And these are the files that will be written. So I will be discussing in a short video next time.